Welcome back, everybody. So we're on our, I think, 6th video in a series where I'm learning the programming language Rust. For those of you that have been following me along, thank you. You can tell that I'm still learning, can't you? I'm pretty bad, but I'm learning and I'm getting better. And thanks to you, some of the viewers, for your comments and feedback. You're actually helping me improve. So please keep that coming. So today I wanted to go through and take where we sort of left off and build on top of that and turn our program into something that parses fits files more completely. For those of you that remember, there is a GitHub repo which is called Fits Rust. You're more than welcome to go along and sort of have a look at the source code. The source code that's there is where we left off last video, and every time I upload a video I also push updates to the repo. There's a markdown file that sort of describes what we're trying to do, and you can sort of follow along there and get a sense of the scope of what we're doing. Now, for those of you that haven't been following along, what I'm doing is I'm building a Rust program that will be able to parse and process FITS data. And FITS is a common astronomy data format used by, well, it was invented by NASA, and it's kind of commonly used. But it's also a fairly archaic or a fairly old format. I dare say it'll be replaced at some point in the future, but it is commonly used and it's widespread. And there's a specification document here. This is the version 4 spec, and it sort of describes the overall file structure and organization, how to parse headers and the data units and extensions. It goes through it in quite a bit of detail. And so we've started looking at this, but today we're going to spend more time just making sure we understand what this format is and how to understand it. So what we'll do is we'll go back to the program that we wrote last time. I'll cover it really quickly here. We had an enumeration that represented state as we're going through and parsing the file. It was kind of like, a really simple state machine, if you like. It's probably not it's stretching it to call it a state machine, but it represents state. We had a struct for records, which were key value pairs in the header, separated by equal signs, and we had some constants that are defined in the spec. So a block size, we read 2880 bytes at a time, and then also within the header we were reading 80 bytes at a time, and that was kind of a record. Anyway, and so then in here we do some command line argument parsing and handling. We have a default fits file. We've also got data inside of our project, which is our example data files that we're going to use, and that will be test data for us. And then we read the file in its entirety, put it in a vector called fits data. Anyway, and then we go through and we start basically going chunk by chunk, which is an improvement that somebody recommended. So we use dot chunks on the vector, and then we do that by block size. We're stepping through by 2880 bytes at a time, and then we run this match across what we get back. Now, there's lots of improvements we're going to make to this today, especially this part of the parser, the simple parse that we started writing. We've got some ancillary functions to parse the header and the data and so on and so on. So anyway, that's where we start. That's where we left off. So we're going to start here today. We're going to make a ton of improvements. I'm going to be quite ambitious. We've got another hour, let's say, and I'm going to try and go through as much of the enhancements I can do in the hour. And I'm going to try and kind of complete the parser, loosely complete the parser, and then I'm going to try and also start rendering the data. Now, we may not get to image display, we'll see how we go, but we'd better dive in. So the first thing I'm going to do is I've been looking at the feedback again and realized that we don't need to stringify at all. So what I was doing here is what I typically do in another language. Here I was taking a slice of bytes and returning a string, and this generated and built a new string. This into-owned function basically extracts the owned data out of this clone on write structure and builds a new string and clones it if the data is not already owned, and basically returns a new string. So this is kind of expensive, right? Expensive is a relative term, but it's building new strings which are stored on the heap, so it's not memory, it's not sort of memory efficient, and it's also just kind of slow, potentially. Well, it's not going to be that slow, but anyway, we want to make our program as fast as possible. And so we use it here to stringify this record when we're parsing the header. We're using it up here when we're trying to look at whether or not something contains particular patterns. We're doing that again for extension. We're doing it here for the header. Anyway, so it's used a bit. And so what I want to do is kind of collapse that, because this this clone on write structure is really cool, and I didn't understand it. But what it does is it returns a structure that when we're reading from it just gives us a read-only version of the string. But when we want to mutate or update the string, it clones the underlying string. And so it gives us kind of like a mutable version. Back when I was doing my uni many years ago, we did Copyonwrite to allow multiple readers for read-only data in parallel, and then every time you'd mutate or change a data structure, you would clone it, and we called it, or copy it, we called Copyonwrite, so that basically every subsequent reader would read from the new cloned version. And so as readers went away, you'd kind of just get rid of the older, copied or cloned versions of the data structure. It was a nice way of kind of trying to parallelize access to an underlying data structure for multiple reads, but single writes, and then, multiple writes, but you'd sort of clone. Anyway, and so what we're going to do is we're going to get rid of this altogether, because we can just use the copy on or the clone on write data structure everywhere we need to use this string, and we'll update some of the signatures. So let's go and do that. So we're going to basically mark where it's used. It was used here. So what I'm going to do is go string from UTF-8 lossy record. Okay, that actually works. Now it causes problems for parse record, because parse record expects a string, and now it's this copy on write structure. So we'll actually do that. We'll change it to this copy on write structure, which will now throw an error because we're not importing it, but that's okay, we can fix that. And so we'll go through and we will, oops, what am I doing? We'll go through and we'll just update all the references to stringify. So just bear with me while I do that. Yep, from UTF-8 lossy right. And now to fix that copy on write, I think it's use standard borrow. Is it lowercase borrow copy on write? So that should fix that. Cool. And so now we can actually get rid of the stringify function altogether, because we're not using it anymore. And so effectively we're not building strings anymore, and we can just do dot contains. We can do all our pattern matching and what have you using that clone on write structure. And so when we use it, it'll return a read-only version of the string, and we can just call dot contains on it, which is really neat. All right, so let's just make sure that our program still compiles. That's always a good thing to be able to check. And happy days, everything works. So that was the first really simple thing that we wanted to fix. Now let's go and have a think about what we're doing here. So if we go back up to where we were defining some structures and our enum, what I'm going to do is rename this thing to just section, and what I'm going to do is I'm going to get rid of this crate fit section glob, which imports all the members into that kind of local scope. And the reason for that will become clear in a second, but it does mean that I'm going to have to kind of fully qualify here. So I'll just add section. I'll get rid of this as well. Section. Which is a bit of a pain. Well, it sort of looks at it. It's arguably more readable. And we're going to kind of do something different that will use those names again. So I want to get rid of that. All right, so that's fixed. All right, now what I also want to do, so some of the feedback I had from the last video was that I don't need to use map, and this, I was using map with this closure, and I've got a tuple here for I and chunk, where I was the count through the iteration. And so what I'm going to do is I'm going to get rid of all of this, because actually I don't need to define this unused chunks variable, which was a vector of unit. And so what I'm going to do is kind of just go back to for, and I'm going to call it current block instead of I, and I'm going to call it chunk still. I could call it block, couldn't I? I'll keep it as chunk. So I can do for current block chunk, and then dot chunks, dot enumerate, and then I don't need any of this. And I'll use a for loop to get rid of that. It's already becoming more readable. And I don't need to do dot collect because I'm not using this lazy map thing. And so I've now just got a for loop, which looks a lot cleaner, except for in what was it? Fits data. Okay, so so that's better. So I'm now saying for current block chunk in fits data chunks enumerate, run this loop, and it's basically going to loop through, and I better update here and call this current block, and then I'll do current block here and here as well. I'm sure there's a better way to do this, but anyway. All right. Oh, no, still got one here too. Don't refactor your code this way, guys and girls. Do a search and replace, maybe. All right. So this should give us what we want from a for loop perspective. Now, this is a bit cleaner. The other thing I wanted to clean up was this for loop. I was still using this old school enumerate step by, which I don't want to use anymore. So I'm going to do the same sort of thing. So for I, and then actually, do I need I? Am I using it anywhere? I won't need it. So I can probably just do for chunk in data dot chunks, and the chunk size is still record size, remember, which was that 80 byte thing. And I can get rid of this altogether. Now I've just got a nice for loop. Now I don't need this anymore because the chunk contains the slice that I want, and I can just do this. So the record string is string from UTF-8 lossy of this 80 byte chunk, which gives me this clone on write thing, which looks really nice. Then if let some record key value parse record string. Great. So let's just uncomment the print line and just make sure that this still compiles and gives us what we want. Yep, it does. For those of you that want to check, I think that was the data structure we were using. And the last couple of key value pairs in the header is sequence name. Nice. Yeah, looks good. So, so that's a little bit cleaner as well. And we've got a little bit, the code is looking a little bit better. Now, what I want to do is I want to sort of probably improve the way that I'm doing my parsing and storing the results of the parsing. And so if you look back up here, we've got this enumeration, we've got structs. What I'm going to do is I'm going to define sort of like an overall struct for what a fits data thing looks like. And it's going to have, the type of it's going to be header, data, and extension. And it's going to have a header of type header. Oh, I'll just do this. It's got a header. I'll do this, yeah. Header of type header, data of type data, extension will be, let's make it a vector of type extension. Oops, so we'll do that. Okay, and so what we're going to do is create these structs. So we've got a struct called header, and a header, and a header contains a hash map. So what I want to do is give it a data member and say it's a hash map string. And I think that's all data needs. And then data is going to be, this is going to be funny, but I'll just say data is a reference, or it's a slice of bytes. Now, because I've got a, because I'm sort of borrowing here, that's kind of what this means in other languages like C or C++, it's a reference. But I read this in Rust as borrow. And because we're borrowing, we need to specify the lifetime of this, this data. And so the way to do that in Rust, and I'm not going to go through it in detail, is to use this notation and then sort of basically mark this member as, oh, I think, what have I done? I've got the syntax wrong. Unused parameter. Yep, I think maybe it's after here. Yeah, so this is basically just going to say that the lifetime of this reference is kind of, the way I understand it anyway, without really having gone through lifetimes in Rust very closely, is that the lifetime of this data, or the value of this member, is going to be coupled to the lifetime of the struct, and so don't delete one without the other, kind of, you know, manage those together. And then we're going to have a struct called extension, and all that's going to be is probably a string. Oops, that was clever. So yeah, so now we've got a little bit more data sort of structure here. So we can start, when we're parsing, we can populate the header and put the hash map in there, likewise with data and extension, but then we can sort of wrap it all together inside of a fit structure, which, I don't know, sounds nice. Let's see how we go. We're going to get this weird thing here where we'll have sort of fits.data.data, which is not a great API or interface, but whatever, we'll sort of deal with it. And so what this means now is within this scope, within the scope of the main function, we can have a variable called fits, which is basically a type fits header, data, and extension, and that equals, we can actually build it here, and we can say the header is, we'll give it a default value, and likewise we'll just do the same thing for the other members. And so now we've got this fits thing that we can pass around and use in our code. Now it's complaining that it doesn't know how to give header and data a default value for the header and data type. So it doesn't. So header is of type header, right? And data of type data, capital H and D. And Rust doesn't know how to give it a default value. Now there's something we can do here which kind of instruments, or I believe we can derive default. Oops. There is a way of deriving default. I'll have a look at, well, anyway, let's just see if it tells us how to do it, otherwise I'll just Google it. Yeah, so this is kind of like a annotation that we can make on the struct, and it'll basically tell Rust, which one was it, header and data. So we can just go, we can just go, that's cool, here's an annotation, and then it'll do what it'll do its best to kind of derive default values for these types, which is great, and it means that we can do this sort of thing safely. I don't know what the default values will be, but the Rust compiler will work it out, apparently. So anyway, that's cool. So now we've got this fits thing, and we can start stuffing data into it. What we need to do is change the way that we do the parse header bit, because here we've got if it contains end, parse the header, and we've got some complicated looking thing here. And same with the data, but the data we're not doing anything with it. The header we're not actually, there's no side effect, there's no return type, there's nothing. And so we're kind of just doing useless work. So let's change the parse header function to just take the key things that it needs. So what we'll do is parse in, obviously, fits data, and then what does it need? It needs block index. No, it doesn't. Maybe it does. It does. It needs block index, and it needs current block. But the block index is kind of like the last block that we matched on when we found something in our state machine parser, and the current block is where we are, and the rest we can derive and work out. So let's take that. Actually, I'll just do that. Oh, and then what we want to do is put this in the header, right? So we should just be able to do something like fits.header equals. And that should just stuff it inside of our fits struct there. Anyway, so what to make this work, we need to change this. Firstly, we need to return a header, all right? Oh my goodness me. Oh man, sorry guys. Let me just fix this. All right, I'll paste that before I lose it. So what we'll do is we'll return a header, and then let's just call this fits. And what else did we pass? We passed whatever the current block, the last block was, so we'll call it last block, which was use size, and then current block, which was use size. And that should be enough. So we should be able to do something like let header data equal this thing. Which should be accurate. No, that won't work, will it? Block size, block index. Should be block index times by block size, shouldn't it? I believe. So it should be from, oops. Should be, sorry, last block. Oh my goodness, I've got to rename all this. So last block to last block plus the current block plus 1. No, that's just wrong. Should be something like this, I think. And then, so we basically want to go for the last block times the block size, which gives us the index into. If last block is 0, then that's fine. And then, which it will be for a header, and then current block will be where we were up to, plus 1 because we were looking at matching end, and so we want that block, times the block size. That should give us the range and a slice, I think. I don't know. We'll work it out. Right. Let's see what happens anyway. And then that header data, so we'll still print that for a bit of extra stuff. So we need to call this fits, not data. What else is wrong with this? So for chunk in fits, for chunk in header data, chunks record size, record string equals that. If we can parse it, great. If not, great. So what's it complaining about? Mismatch? Oh no. Found. I'm impatient. Let me just see what it says. Expected header. Oh, so we need to return a header. No joke. So what we'll do here is we'll just put the data is the hash map, so we'll just call it header records. Yes. Cool. And so this should be enough because Rust is really cool. We don't need return. We just put the last, whatever it finds as the last statement. Do I need to sort of just do, probably don't even need that. Kind of cool. Don't even need a semicolon. All right, so this thing now should construct a header struct and put header records, which is the hash map that we're populating by doing this parse record, put it in the data member and return it. And so we've got a header now. And so back up in here, we should be able to go parse header and happy days. Oh, it's complaining here. Yep, because it's not called fits data anymore, is it? It's called something else. Oh, no. Fits, plural. All right, cool. So that's now the header. Now, what we'll do is we'll start parsing the data. So we'll improve this, and we'll do the same sort of thing. So we'll just say we only need to pass in fits data, and then the cool thing about the data blob is that it should be well known. So we should know the dimension or the number of dimensions in the data, and we should also be able to compute that. So what I'm going to do is say that we'll call let dimension equal some magic number. No, we'll say, let's say dimensionality. Is that a word? So we'll say let dimensionality equals 2. Let x and y equal 2002. Do I need to define the, no, even further type, cool. And then what we can do is we just say pass in, so we'll pass in fits data, and then we can compute the rest, I think. So all we need to do is do sorry, I'm just thinking about this, something else. So all we need to do is just pass in the x and the y tuple, I think. I don't know, something like that. We'll work it out. So we'll go into parse data and we'll just put this thing in just so we don't lose it. Don't ask me why I'm doing it like this. And then parse data will give, well, it currently gives us usize, which is useless. Sorry, what I was thinking before was the way that I'm incrementing block index. And block index equals current block doesn't work because we'll need to add one to it. Because the last block that we match is the block that contains n, which is still part of the header, and we need to go one past that. So it should be current block plus 1. All right, so let's go back to parse data. Now fits data should be fine. I think that's all we need, isn't it? Now we need to go and read this out of the header, and we'll do that, but I think that's enough to start computing how to read this thing. So what we'll do is we'll say let data, let's call it data. We'll call this fits again. So let data equal, and then fits. Actually, sorry, let me just do this. So we'll pass x and y in here, which are, what are they? Does it tell us the type? Type error, that's really handy. I don't know, I'll just call them U32. So we'll do this, and then we'll say let data size equal x times y in bytes. And so it won't be bytes, it'll be, yeah, okay, this is gonna get interesting. So to do work out data size by, it'll be basically however we need to interpret the bytes in the data block. And that could be, that'll change depending on what the header says. So if the header says that they're 16-bit ints or 32-bit floating point numbers or whatever, then we'll need to know the width of the data unit, if you like. So I'll just call it that. So we need to work out the data size by data unit. So if it was 32 bits, then we'd need to do times 4. But we'd need to compute that instead of hard-code it clearly. And so parse data would probably need to know that. Either it would work that out from the header, or we'd pass it in the signature as an argument. Anyway, so we'll do it like this for now, and we're going to go. It is. Oh, we need last block, don't we? Yeah, we need last block. So let's pass. What do we call it? Not last block. Block index, which was the last block that we read. So here we've got. Last block. We'll call it last block. That makes more sense to me. Probably what I should have called it. And we'll give it usize. And so here what we can do is say, go from the last block times by the block size to basically the data size plus the last block times by block size. Something like that. But of course this is freaking out. Found it. Okay, expected use size. Oh, because that's U32. Okay. Oop. Can I just do this? Can I say data size as usize? I have no idea if that works. And anyway, what did I have? Oh my god. What did I have? Block index. This is all wrong. Okay, so that's just wrong. Alright, so this should give us the blob of data that we're after. From the last block times block size. So the index into after the header basically, and then whatever the data size is along, I think. No, that doesn't make sense because data size is the number of bytes. So we don't need block size. Oh my goodness me. Should just be that. Okay. So that sort of looks better, doesn't it? Anyway, we'll find out. And so then what we want to do is we want to return a data struct with the data in it. Oh my lord, that looks terrible. So we'll just call it data. What can we call it? It's the data block, data unit. Let's call it data unit. Because there's too many datas going on here. All right, and so this thing doesn't return a usize anymore. It returns data type, and that's kind of data done, sort of, kinda. But it's not data size anymore. It is, we want to do fits.data equals that. So that's starting to become a lot more interesting, except fits isn't mutable, which it clearly needs to be. And likewise up in header, whoops, I didn't do this, did I? So I need fits.header equals parse header. Cool. Now dimensionality, we'll work that out later. Well, so what we're going to end up doing is something like this. Alright, and so we're going to say, we'll basically interrogate the header. If it's two-dimensional data, then we'll get the x and y coordinate, and we'll interrogate the header to get that as well, or the dimensions, x and y dimensions. And then we'll do this parse header business, which will then let us populate fits data. Anyway, and then we'll say we're going to look for an extension next, and then the block index will be the current block plus the size of the data divided by the block size, which sounds a bit complicated, but basically this will be the number of bytes that we've read, and we want to divide it by that to get the number of blocks effectively in the data blob and add it to the current block. And I'm not sure if we need a +1 there. Don't think so. So if we read 2,880 bytes, then we're just going to have current block +1. So any multiple of that should be okay, shouldn't it? So if our current block is like block 3, and we read another block, then the block index becomes 4. Should be fine. Anyway, I don't think we're off by 1 or anything there. All right, and so the next thing we want to do is fix this extension thing. And again, we've got all this stuff, which is, if string bar contains extension, found it. Yeah, this is all buggy. We'll fix that at some point, I guess. This looks way too long. Anyway, and then if it contains n, we'll parse the extension. So again, we want to do something with extension. Again, I think we'll just keep it simple and just pass in fits data. And then what do we need? Block index and current block, I think. So block index and current block. And then we can just get rid of this thing, go down into our extension function, and then we can say let extension data equal, I'll call this fits again, and then we had, was it last block and current block. I think that was right. And it's going to do something like this, isn't it? No. It's going to be like the header, I think. Oops. So I'll do extension. So does that work? We'll take the last block times the block size, and the last block was set by here. There. And we go to, whoops, and we go to the current block. But we don't need +1, I don't think, do we? No. I think it's just this. Ugh. Anyway, well, let's give this a go. I think that's okay. Oh, but the thing it needs to return, of course, is an extension. Extension. And then this thing just needs to return, we just need to build an extension. Should be enough, I think. So, cool. Let's see where that's used again. So, now what we're going to do though is we're going to push that. Push. Something like that, I think. So because extension is a vector of extensions, fits.extension is a vector of extensions, and this parses one and returns an extension, so we push it onto the vector. I think that's okay. And then we do block index equals current block plus not +1. Is it +1? It is +1. Okay. I think that's right. So that, because we're matching end in the string, the last thing we read. All right. What the hell is it complaining about here? Mismatched type. All right. So we've got a slice here of bytes, and we need a string. And good call. Let's just do string from UTF-8, our favorite function, with the extension data, but that will be a copy on write. So to get a string, we'll call to string. Sorry, clone on write. Got to get that out of my head. Yeah, we need current block plus 1 times block size. Tell me? Current block times block size. No. We'll work it out. In fact, I don't know how associativity works here. I don't think we need any of these brackets. Because I believe that should work. All right. So now we've got something that we think should work, and I'm being terrible because I haven't even tried to compile this program since the last time I ran it ages ago. Right, so now we're way off, okay. All right, so let's just see, we've made some assumptions. How big is our data? It was 2-dimensional, and it was 2000 by 4. And I said it was 2000 by that. And then how big, so it was 32 bits. So where did I make my assumption? Stop hard coding, dim, and look up in header. But I'm lazy, I just want to try and get something working. So same problem. So we're getting sequence name. All right, so that at least works, but let's try and do, let's try and, now we've got this fit structure, let's interrogate it. So we should be able to do stuff like print line, I don't know, what do we want to print? Let's look for the size of the data. Size of data unit, and then it'll be fits.data, this amazing thing that we've built. So we'll print that, and let's do maybe extension. Do we want to print it? Let's try and print the extension data. So it'll be extension, but it'll be the first one dot data. What's this complaining about? Oh, okay, it's fine. So this should give us, I guess, the number of bytes that we've read, which should be 4 times this thing. 4 times 8, so it should be 32,000. Maybe we can do in parse data, we can do something like assert that data size is equal to data unit length. Do we get length? 2vec. I have a feeling I'm doing something really stupid, but anyway, we'll do that and see. That should be the same, shouldn't it? Copies, data unit. Can't I just do length on the slice? Why not? I can. Cool. All right, great. All right, so that, anyway, I mean, that's obvious given that we've constructed this thing, but anyway, that gives us some confidence. Cool. And then, yeah, anyway, so let's see what this does. Error. Great, we've got errors. So left and right. Oh gosh, it's way off. So that's that's interesting. Data size X and Y. Is that the assert doing that? Must be, yeah. Whew, whatever that was. Whoa, what the hell just happened then? Got all this binary data. Ooh, doesn't look right. So the extension contains way too much stuff. So last block is wrong. I'm just going to be superstitious. Let's see what happens here. Oh, still giving me way too much stuff. Bummer. So I was right. Anyway, that's not good. We'll work that out. Plus extension. Block index. Current block. Plus fits data length divided by the block. Well, anyway, let's see how much data we've read. So I'll basically, I'll just print this, and I'll just start saying data length is data unit dot length. Ooh. See what happens here. Oh, that won't work. Ew, that's totally wrong. What is going on here? Last block times block size to data size. Last block. Huh? What am I doing? Wow, I'm so dumb. So it's basically that. Guess. Didn't write. Ooh, what have I done? Screwed up. Okay, let's see. So we've got that. That looks better. Yeah, so I was computing that wrong, like an idiot. So now we should have something that works. And we should be able to just know that that assert works. Happy days. Now let's see if we can print the extension. I have no idea if this, yeah, so that's wrong. But why is it wrong? Fits extension dot data. Fits extension, parse it. Is it +1? It's like we're getting a whole bunch of crap here at the end. So this is kind of like, I don't know how many bytes is here, but it's not 2880. So we're getting an off by something error here. So the extension data, so pretty sure this is wrong. Let's see. Off by 1. If in doubt, add 1. I don't know. That seems annoying. Anyway, all right. So we've got it now. So we're now we've got the size of the data. We're able to get the extension. We've got data that we care about, and we're making some good progress. Just checking how much time we've been going for. So 50 minutes thereabouts. So let's see what we can do in the last 10 minutes. I know I've been jumping around quite a bit. I'm starting to become a little bit more comfortable in the language, but doesn't mean I'm still not making lots of mistakes. All right. So we've made a whole bunch of hard-coded assumptions here. So we could either start reading the header to pull those out and generalize, or we could forge ahead and try and do something with this data. And I'd like to try and do something with the data, to be honest. So what I'm going to do is I'm going to say, I'm going to create a new thing called render data. And it's all we need to pass, I think, is fits. And render data is going to be responsible for so it's going to interpret data based on header values. All right, we need to jump into the spec quickly. We need to double check what these header values are. So I was jumping around earlier and I had Naxos was equal to 2, which means something. Naxos 1 is 2000, Naxos 2 is 4, and then we had extend equals blah, right? And there was this other thing called bitpix, which was negative 32 that said 32-bit IEEE floating point. So that tells us, I think, about the data. Now what we need to do is go and check out our spec. And we went through this in previous videos and we worked out that fits had a primary header and data unit called an HDU. It optionally had extensions and these special records. And then we were going through and sort of looking at the first fits file will be a primary HDU, and if it has 0 length as determined by n-axis and n-axis n in the primary header, then the primary HDU shall, it's like a commandment, contain no data blocks. So what we want to do is, and so what is it? So the primary data array, if present, shall contain a, so it can have 999 dimensions as specified. So yeah, so n-axis defines the dimensionality of the data. So the dimensionality, or the number of dimensions of this data, is 2. This could be so this is like a x and y plot. It's probably an image, and then there could be cubes where the n-axis would be 3 data cube, and then there could be 999 dimensional data in here, and my mind explodes trying to even understand that. But what's n-axis? So the index count along each axis shall begin with 1. So n-axis n. Okay. The individual data values shall be stored in big endian byte order, such that, yeah. So it's big endian network byte order, makes sense. Lots of data formats use big endian byte order. But what we want to do is, okay, bitpix was this one. So bitpix, the value shall contain an integer, shall, but it's a signed integer in this case. The absolute value is used in computing the size of data structures. It shall specify the number of bits that represent a data value in the associated data array. The only valid values of bitpix are given in table 8. Right, so here we've got a table of how to interpret bitpix, and minus 32 is single precision floating point. So it's 32-bit wide data, and that's because it's single precision. So you can do double as well, which is 64 bits wide. Okay, so we can just use Rust's F32 data type, big endian. Now this is good. So n-axis n, so these keywords must be present for all values n equals 1. and then a value of 0 indicates no data. If it's equal to 0 there, okay. But it's not. So we'll just make some assumptions. So we know that's 32-bit wide, single precision floating point. Okay, good. So what we need to do is interpret this data. Now, so this is where it gets a little bit more interesting, I think. All right. So what I'm going to do here is I'm going to say print line. Let's go for rendering fits data. Just check time. I think we're almost at time now, unfortunately. We've got a few minutes, and we're going to try and keep it to about an hour. So what we need to do is read the bytes as big endian 32-bit single precision floating point numbers, which is fun. And I'm not going to try and do that myself. I'm going to use a crate. There's a crate that I want to use called byte order, and let's have a look. Rust byte order. Look at in crates.io. So crates.io is awesome. It's where all the crates are kept for Rust, and so I can just take this and put it in my toml file, and just do that. And then the next time I compile, it will go and download the byte order crate for me and do magic. So here to use it, I do extern crate byte order, and then I specify how I'm going to use it. And so at the top of the file, this will be our first, this will be our first external crate that we've used, which is kind of cool. So we'll say extern crate byte order. Yeah. Cool. And we'll do a use later. Cool. That's great. All right. So let's save that. And let's just build and see what happens. So, oh my goodness. So I'm just going to do cargo run. It's going to compile it. Oh, it's going to complain too. That's great. Render fits. What have I done? Oh God. Okay, so so render data, and then it should just expected slice. Oh yeah, such an idiot. So that's a fits thing, and it's got a header. Oh my goodness. Data extension. And I can't type. I think this is a sign the video is getting too long. Oh goodness. No. This fits, right? Oh, but I'm gonna do a reference. And it's just read only, we don't need it to be mutable. I'm gonna just get rid of these lovely things, these print lines, we don't need any of that. And so we actually get what we want. I'll get rid of the header print line as well, which was down here somewhere. Parse header. All right, so just prints out a bunch of stuff. I'll get rid of the debugging at the top as well. Cool, and so this thing kind of does what we want. Byte order is there, we're not using it. So let's go and use it. Now, I should be doing a whole bunch of checking in here. So I should be doing check bit picks. If it's 32-bit, then do stuff. But what I'm going to do for now is just make some assumptions. So I'll say use byte order, and I'm going to use two things from byte order. I'm going to do big endian, and I'm going to do byte order. And that will import those two functions for me. And then what I'll do is I'm going to try and use it. So I'll do big endian, and then there's this read from, I think it's read F32 into, gosh, is that what it's called? I don't remember. Read F32 into byte order. Here we go. Looks all right. It's cool. So reads 4-byte floating point and does stuff. It's kind of what we want, I think. Big endian. So we need a source and a destination vector. And so the we've got the source vector. The source vector is fits.data.data, but it should be a reference. And then the destination is whatever we want to call it. We'll create a new vector and we'll call it converted data. We'll just call it rendered data. I don't know, it's a terrible name, but we'll create it. It's a type vec of 32, F32, so floating point 32-bit floating point number vector, and then we'll let's just see if we can do default. I don't think this will work, but then we can just do I think we need to do a mutable borrow rendered data, rendered or data for the US people watching this. So rendered data, and then I think that should, so what this should do is it should use big endian byte order, read from bytes in this vector and treat them as 32-bit floating point numbers and write them into the rendered data. And that will do kind of the endianness for us, and also turn them into things that we can actually kind of display. And I think that should break. Okay. Okay. So this thing actually panics if the length of this is not the same as the length of rendered data. And the length of rendered data is 0 because we've just said default. And so what we need to do is we can use this shorthand notation to create a vector, and we can initialize it with zeros, but we need to make it a certain length. And that length will be whatever this thing is divided by 4, I think. Because we're reading 32. Yep, great. So it's rendered it. Beautiful. So I think that might have worked, which is kind of a miracle. Now, what we're going to do is, I think we're at time, and it's really a shame because we made some good progress. But what we've done is we've read the data, we've converted it, and what we now need to do with it is we need to do something like, we're going to have 2 more functions in here. We're going to have like a write. What are we going to do? We're going to do a data stretch. So we're going to stretch the data for rendering or visualization. And then, so that will be something like, you know, I don't know, we'll just call it a data stretch or something like that. And we need to normalize it as well. So we need to normalize and stretch. So we'll have some function that does that, and then we'll also we'll write the data out, and so we'll do like a write PNG type thing. We'll say write the data as a PNG or a bitmap or something like that. And so we'll get into this in the next video. I thought we'd get close to building an image, but we're not quite there. And also we're making lots of assumptions we need to go and fix as well about things in the header. But we just want to try for our simple data example, we want to just try and render something. And the reason we're normalizing is because we're going to have data. It's basically going to be these floating point numbers are going to be all over the place. They're going to represent kind of the magnitude of the light that was hitting the detector and the camera, and it's a charge coupled device, I think, on the Hubble Space Telescope, a CCD camera, or a number of them, and so it's going to be able to see and register magnitude of light or light energy that's far in excess of anything the human eye can really interpret and understand. And so what we're going to do is we'll stretch the data, and I'll get into that in the next video, and we'll apply kind of like a we'll take the histogram of the light and we'll basically squash it. So and then what we're going to do is we'll then turn that into sort of values, into grayscale values from like 0 to 255, and then we'll render that, and it'll all become a bit more clear because I need to go through probably a little bit about the physics of, well, not the physics, but the way that the eye sees compared to the way that, say, a camera like the cameras on the Hubble Space Telescope can see things. But we're getting really close. We've now, if we look at what we've done, and we're a little bit over time, we've now got a much more a more interesting way of storing the data in this fit structure. And we've got a header data and extension struct with the record struct there of the constants. We're parsing, we're reading, we're parsing, we're pulling out the header information, putting in a hash map, we're parsing the data, and we're even starting to render it and interpret it according to the data in the header. We're pulling out the extension as well. It looked as though in our example file there was also, after the extension, there was some more data. Yeah, there was this blob. So that looks like it's one of those special things. And so we'll probably try and work that out as well. But anyway, and then now we're getting into the nitty gritty, I think, of actually doing something interesting with the data. So heaps of progress. It's coming along. And so I'm going to stop there, and I'll upload this, and I'll push this code to the GitHub repo. Please feel free to clone that and do what you want with it. But look, I hope you're enjoying it. I'm kind of enjoying it. I'm kind of learning more about Rust and enjoying it more. I'm sort of learning to be, I'm quite interested in Rust. I'd love to take this language further as I get a little bit more, a little bit better at the language. But anyway, and so I guess my main call out is if you are enjoying this, or you enjoy just laughing at me fumbling around, then please subscribe. I'd love to build a bit of a community of people around this stuff. If you're an astronomy geek or a data geek or a Rust geek, please subscribe and like the video if you liked it. If you're an expert Rust user, and there are a couple of you that are already starting to watch, thank you for watching, and then also thank you for your feedback. It's been really constructive, and I've learned a lot by sort of reading about the comments that you've made, and hopefully I'm folding that and taking that feedback on board. Anyway, so please join me for the journey if you're interested in this stuff, and I look forward to seeing you in the next video. Cheers.